你點樣開翻？你應該先，因為而家要 share。你想人傾咪定係？得㗎啦。
Okay, so little audio problem, but it's been solved. We're all at the mercy of the technology. So welcome to this second meeting. We are the Research Center for Language, Cognition, and Neuroscience, RCLCN. And it's amazing that almost 3 years have passed because we were established in January 2019. Currently, this is the faculty of the Research Center. There are 7 of us, all in the Department of Chinese and Bilingual Studies. So the 3 terms in the name of the Research Center are intimately related to each other. Language has a central role in cognition, which in turn is enabled by our powerful brain. So we adopt a multidisciplinary perspective in our research on the many themes of language, aligning the humanities with the life sciences. Some of these themes are how native and foreign languages are acquired during childhood and during adulthood, how spoken and written languages interact, how biological and/or environmental factors enhance or impair language behaviors, such as autism, aphasia, dementia, all due to neurodegeneration. We're also interested in how language is related to another fundamental human universal, music, manifested in phenomena such as amusia and melodic intonation therapy. To ground our research empirically, we often use various methods of neuroscience and psychology, including EEG, MRI, eye tracking, brain stimulation, and so on. So in addition to the facilities available in our own Department of Chinese and Bilingual Studies, we also collaborate with the university facility in brain and system neuroscience, university facility in big data analytics, and also the newly established Research Institute in Smart Aging on our campus. These are all our partners. Since the topics covered by our 2 speakers this afternoon are clearly related, what I would like to do is introduce them both now so that there'll be no interruption between their lectures. First, we will have Professor LEE Tan, okay, who comes south here from Chinese University of Hong Kong, Department of Electronic Engineering. His research interests cover speech, audio processing, spoken language technology, deep learning models of speech and language, paralinguistics in speech, and neurological basis of speech and language. He applies signal processing and machine learning, these methods to atypical speech and language in a wide range of communication scenarios. He is an associate editor of the IEEE ACM, Transactions on Audio, Speech, and Language Processing. He was the general chair of the 11th and the 12th International Symposium on Chinese Language Processing, ISC-CSCLP. Professor Lee received the CUHK Vice Chancellor Exemplary Teaching Award in 2004 and the Faculty of Engineering Exemplary Teaching Award for over 10 times. He was invited to teach elite students of the Yao class of computer science at Tsinghua University in Beijing during 2013 to 2017. Since 2019, Professor Lee Tan has been teaching artificial intelligence-related topics to gifted students of age 10 to 16 in Hong Kong. I find it particularly impressive that Professor Lee can so successfully combine his leading-edge research with such devotion to teaching, not only at the university level, but even to 10-year-olds when the mind is just coming to bloom. So he sets a very fine example for all of us to emulate. He will be speaking on synthesizing natural speech with expressiveness and personal style. Okay? And people speak in different styles, which are personal and situational. And proper choice and use of expressive style is key to effective speech communication. Text-to-speech, TTS, is a technology automatically generating speech in accordance to given speech input. The latest TTS systems based on end-to-end deep neural network, DNN models, can generate fluent speech, but are perceptually comparable to human speech. However, for naturalistic interaction, computer synthesized speech is expected to not only be clear and accurate, but also carry appropriate desired speaking style. So expressiveness is largely missing in existing speech synthesis technologies. Being conceptually similar to conventional analysis by synthesis models of speech, the encoder-decoder type of DNN model has been widely adopted for the analysis of latent factors of variation in speech. Specifically, an input speech utterance can be decomposed into components related to linguistic content, speaker identity, and expression style. Control of expression style and speaker characteristics in TTS can be achieved by manipulating the respective embeddings and recombining them with desired content information. So today, Professor Lee will present a few recent studies on DNN-based speech generation with personalized voice characteristics and controllable expression style. Successful application in child storytelling and voice banking will be demonstrated. Following Professor Lee Tan, we will have Professor PENG speaking to us from the Department of Chinese and Bilingual Studies on campus. Professor Peng has a broad range of scientific training, mathematics, computer science, and language sciences. His central focus is to investigate how language is represented and processed in the human brain, and how different cultures reflected in their languages shape perception differently. He adopts a multidisciplinary perspective for the study of language and the brain, with primary focus on the two most distinctive features of the Chinese language: lexical tones in speech and sinograms in writing. He has published extensively in the field of psycholinguistics, neurolinguistics, in various high-profile journals, such as Proceedings of the National Academy of Sciences of the USA, Neuropsychologia, Brain and Language, and so on. So on this occasion, we should especially like to congratulate him for winning the Faculty Award for Outstanding Research, which was just announced this past Monday. Professor Peng will speak on tone recognition, tone perception by electronic brains and human brains, with a focus on the human brain. Cantonese has a highly complex tone system. How to correctly recognize and perceive Cantonese tones is challenging. And in this talk, Professor Peng will first illustrate how electronic brains, that's computers, recognize Cantonese tones, as well as their general error patterns, and compare the performance of recognizing, perceiving two easily confused level tones in Cantonese: the mid-level tone, tone 3, and a low-level tone, tone 6. Secondly, he will show behaviorally how different types of contexts, speech versus non-speech, influence Cantonese level tone perception, and illustrate the importance of speech context for Cantonese level tone perception. Finally, he will discuss the time course of context effect on Cantonese level tone perception using event-related potential, ERP measurements, and a possible cognitive processing underlying these ERP components. So with no further ado, I'd like to invite Professor LEE Tan to come and make the presentation, and there will be adequate opportunities for discussion.
Good afternoon. Can you all hear me okay? Okay. Thanks to Professor Wang for the kind introduction. Professor Wang mentioned one of the courses in Tsinghua University Yao class. Actually, I was having the fortune to travel with Professor Wang a few times to Tsinghua, and then actually we co-taught this course. So that was really a wonderful experience. And I know many of you here, in the audience, Professor Pang, Professor Wang, and Manson, and many others, and also Professor Choi. Thank you very much for coming for today. As Professor Wang introduced, so I'm with electronic engineering of the Chinese University of Hong Kong, and I've been working on speech and language processing for quite some years. So today, I'm going to focus on one area in speech and language technology, which concerns with the generation of spoken language by computers. So I will have quite a number of audio files to play. I hope that, you know, this sort of mixed mode audio-visual system, you know, would not affect, you know, the quality of this sort of presentation. So I'm going to give a review on speech synthesis, which is a very long topic, hundreds of years. And then I will talk about the state-of-the-art DNN approaches for speech generation. So I'm not going to go into the, you know, computer science or engineering signal processing details, but just try to explain the operation principles and, you know, the general principles of this approach. And so regarding the expressiveness and style control for speech generation, the separation of different factors of variation speech is the most important issue. So I'm going to talk about how we tackle this problem. And then also I'll talk about a few examples of style prosody control and transfer and some applications. So as I said, you know, TTS, text-to-speech, is one of the mainstream speech technology, which you see in, you know, a lot of gadgets and everyday devices, mobile phone applications. So like Siri, you got a voice input, and then you also receive voice output that is actually generated by speech synthesis or text-to-speech technology. But the speech synthesis has a very long history. The earliest sort of speech synthesis was done purely mechanically. Okay, I think that was back to 18th century. It's just a mechanical system. And then early in the 20th century, so actually, you know, there were a number of efforts, okay, starting from electrical, and then to computer synthesis. Now here I play you a YouTube clip on the Voda, which is one of the earliest electronic synthesizer. And then this demo was given in 1939 in the World Fair by AT&T Bell Labs. Looks like there's some problem of playing the YouTube. Yeah, so we anticipate all these kind of problems from time to time.
We can't manage work like this. That's why I use Monday.com. My team uses it to manage projects, sales, recruitment.
The machine uses only two sounds produced electrically. One of these represents the breath. The other, the vibration of the vocal cords. There are no phonograph records or anything of that sort. Only electrical circuits such as are used in telephone practice. Let's see how you put expression into a sentence. Say, she saw me, with no expression. She saw me. Now say it in answer to these questions. Who saw you? She saw me. Whom did she see? She saw me. Did she see you or hear you?
She saw me.
So the mixed mode operation, my experience is always never successful. Okay. And so when I did the same thing in a number of other occasions, I usually, or if it's just face-to-face, it's okay, or purely Zoom is okay. But we mix them up as. So as a trained electronic engineer, so let's see how. And then the experience that the safest solution is wire.
The machine uses only two sounds, produced electrically.
Hello, you can. Yes. Then I probably the Zoom audience might have problem hearing the so, and let's give the priority to the so we have to choose, right? So let us just take a quick look. Now this particular video clip is not most important, but we have to get the audio work. Okay, so let's look at this.
Uses only two sounds produced electrically. One of these represents the breath. The other, the vibration of the vocal cords. There are no phonograph records or anything of that sort. Only electrical circuits such as are used in telephone practice. Let's see how you put expression into a sentence. Say she saw me with no expression.
She saw me.
Now say it in answer to these questions. Who saw you?
She saw me.
Whom did she see?
She saw me.
Did she see you or hear you?
She saw me.
Okay, so I guess you got the idea. It's just like playing a piano. So what this lady was playing was actually a kind of electromechanical system. And then now, if we know the basic principle of the source filter model of the speech production, okay, there are two sources on the right-hand side, random noise and oscillator. Then the sound source go through a resonator, and then the resonator actually is a set of bandpass filters, okay, just like Formant, if you have ever heard about. And then the 1 to 10, there are 10 different bandpass filters that can create resonance at different Formant frequencies. Okay, and then there are pitch control with the pedal. Okay, so it's just like playing an instrument. And this lady was trained for a long time to be able to give a show. Okay, I think she was under great pressure of doing this. It's really very high, skillful. And then Professor Wang surely recognized this person. This is Professor Gunnar Fant, and then he was famous in his acoustic theory of speech production. You can check out the book. And then he did a Formant synthesizer electronically. So, and basically can control the position, okay, with two dimension on the Formant position F1 and F2. And this is how the sounds.
How are you? I love you.
Okay, so this is also very famous.
How are you?
Okay, so they are, in the following years, now, Professor Gunnar Fant's work was, I think it's the 50s. And then following that, there are many other trials. So I just could not, list all the names. There are many people. And then this set of works I'm showing now is by computers. Okay, like John Kelly and Louis Gersman in 1961, they used the IBM 704 computer, okay, a computer program to synthesize sound like this.
To be or not to be? That is the question.
Okay, and then a Japanese researcher, Umida.
Once upon a time, there is a king and queen who had no children.
I'm not quite sure whether you can sort of recognize the speech. It's English, it's not Japanese. But having said that, this is, I suppose, the retained audio is presumably the best one, right, for demonstration purpose. Okay. This is the Dennis Catt earlier system.
Text-to-speech systems are beginning to be applied in many ways, including aid for the handicapped, medical aid, and teaching devices.
So I'm not going to play all of them. You can check it out. There are many audio samples on internet. I just play you the last one, which is, the latest non-DNN based TTS that was based on statistical model, which is known very well in speech recognition, that is hidden Markov models. And that was by a Japanese group in 2012.
This is a speech synthesis system based on hidden Markov models.
All right. Okay. I think you can still barely, tell that this is synthesized speech.
This is a speech.
Okay. For Siri, all right, we know that Siri has voice, right? And then different versions of iPhone and iOS, they have different Siri voices. Now here I show you two different versions that are quite different generation of iPhones. One is iOS 9, the other is iOS 11.
Take a left on Rocky Ridge Road, then in 600 feet, the destination is on your left.
Take a left on Rocky Ridge Road, then in 600 feet, the destination is on your left.
The same text, two different versions, iOS 9 and 11, okay? And you might say, oh, it's very good, right? It's quite smooth, but remember that Siri actually doesn't have to talk too many different things, right? Usually it's about answering your question, like scheduling, say like weather forecast, email, or so it's not really a free talking thing. Okay, that can be optimized. All right, so it's no surprise. Now, state of the art, all right, is DNN based, deep neural network based system. So I just first let me give you some numbers. So in one of the system, representative system called Testtron 2 by Google Group, using 25 hours of recordings to train, okay, the system, or because it's a machine, it's a computer system, database system, okay. And then in terms of the mean opinion score, that means the rating, very natural, mean, score 5, complete and natural score 1, okay. And then, so these are the human subjective scores. So the Testtron 2 could achieve 4.5, whereas the ground truth means it's real human speech, original, not synthesis, was also 4.6 something. Okay, so it's very close. Now, but don't just look at the numbers. All right, when you write a paper, okay, you present your results. Of course, you won't say, you won't, you know, you kind of design experiments, okay? You know, you will pick up the best results to present. Okay, and this is the other system called Fast Speech by Microsoft. And then so the comparison between ground truth and also the fast speech is something like 4.3 against 3.8 something out of the scale of 5.0. Okay. Now, audio will be both representative. Okay, so here I got a couple of audios. So I will play this one by one to you. You might, you know, tell yourself, okay, silently that, you know, whether this is synthesized or human.
George Washington was the first president of the United States.
I play it again.
George Washington was the first president of the United States.
Next one.
Peter Piper picked a peck of pickled peppers. How many pickled peppers did Peter Piper pick?
You want to try this? I'm sure whether this is human or synthesized, you know, it's much better than what I can do. Okay.
Peter Piper picked a peck of pickled peppers. How many pickled peppers did Peter Piper pick?
Okay, next one.
Others who arrived just after the time of distribution were often 40 hours without food. The latter might also be 6 days without meat.
Okay, the next three, they are all 普通话. Okay.
他非常苦恼，坚持自己原先的主张吧，市政官员肯定会另找人修改设计；不坚持吧，又有违自己为人的准则。
Okay, next one.
伴奏抓紧团结拉拢疲劳的草率。另外，在这儿还是要提醒一下各位考生哈，还有7类物品是禁止带入考场的。
Okay. So what are your assessments? Okay, so this is a good examinee. Okay, so he knows the tricks, right? Right. So you know, in view of limited time, so yeah, these are all synthesis, all of them. Okay, the first two English one, they are by Testtron 2. Okay, the third one English is by Fast Speech 2 by Microsoft. The other three, they are all from a system by our group. Okay, but on different domains. Now you can tell the middle one is actually semantically nonsense, right?
伴奏抓紧团结拉拢疲劳的草率。
伴奏团结拉拢疲劳的草率。So what's that? You know, so you can do whatever you want because it's synthesis, right? So I'm not going to say this, you know, fluently because it doesn't make sense. You know, and also the Peter Piper. Okay, so you know, computer can do very well. All right. So these are all synthesis.
Others who arrived just after the time of distribution.
Okay. All right, so let's move on. So how we do speech synthesis? We talk about source filter, right? Simply speaking, you know, speech signal generation is just to emulating a human speech production system. All right, so it's a acoustic tube resonance with some, you know, 2 different types of excitation. All right. And, you know, all these control are from our brain, and we don't know how to do it, how our brain is doing that. But, you know, in terms of the operating principle, we know that we have to control the frequency response of our vocal tract. We have to control the vibration frequency of our vocal cord. We have to control the intensity, and probably we'll have to make a choice between voice and unvoiced signal, okay? And then, so traditional acoustic synthesis by source filter model, which has been, in your daily life for so many years, okay? I mean, not for the younger generation, okay? For me, okay? So like the old generation GSM phone, okay? They use speech compression algorithms all based on this acoustic synthesis, all right? So it's to having a periodic pulse train for voiced sound passing through resonance filter with a spectrum with several major Foreman peaks, and then to generate a session of sounds. And then they connect, many time frames of sounds and make a long speech utterance. All right, so this is how in the older days we did that. And TTS is more than speech synthesis. TTS starts from text. All right, so one of the most important part, in the text-to-speech system is the text analysis module. So you just imagine that on the left-hand side, the text is a sequence of Chinese characters with punctuations, right? Now, how we make it be audible and then smooth, natural, even expressive, say 普通话 or Cantonese speech. We need the intermediate representation. We just call this linguistic representation, but it's more than linguistic, I suppose. All right, but this sort of linguistic representation in the middle must carry enough information, okay, that can specify the properties that our desired synthesizer speech. So what are those information? Say, for example, at sentence level, we need to know how long the sentence is. We need to detect the punctuations. Phrase, we need to know the intonation. For word part of speech, syllable is stress, lexical stress, lexical tone. And for phone level, manner or place of articulations. These are all the features that we need in order to produce a speech, right? How do we know, father, the R is, different from, R in another context. So we have to give the system, we have to let the system to know the information in order to synthesize them correctly, right? Desirably. So text analysis, speech synthesis, traditionally, they were divided into two different modules in a computer speech synthesis, text-to-speech system. We need to do the text analysis first, and then we feed the results of text analysis to the speech synthesis system, and then we can generate the sound. All right. And then this is, so don't be scared, okay? So I'm not going to talk about these algorithms. So basically, you can view this as a general principle of what we call a statistical model, the speech synthesis system. Now, you just view the graph from the top. X, you can just take it as the signal, the waveform, okay? And W, the big W is the text transcription of this speech waveform. Makes sense, right? Okay. And from the signal X, we do some, they call it vocoder analysis. It's actually like you computing a spectrogram. Now, if you have ever viewed a spectrogram, okay, in your phonetics class, for example, and then L is the linguistic representation from the text, right? So I'm happy to see Professor Wang today. Then, happy, okay, in the middle, if the linguistic feature is that it's a two-syllable, and the head is the first syllable, P is the second syllable, what are the phone identities. So all this sort of information necessary. That is the L, okay? And then with a lot of pairs of X and W, okay, we try to say, I will use the word training many times, okay? Now, I hope that you can bear with me or you get used to that. That is the process of how computer learn the relations in data. That is training, okay? So we train a computer model. So just admit everybody. Okay, and then we got a lambda. Lambda is a model. You can consider, you can just take it as some kind of abstract model library in your computer. You save it, okay? Then from this lambda, okay, it will be able to generate, new spectrogram, okay, based on the text. Okay, the small w means when you really would like to use the system, say I write I am space happy HAPPY to be here. So this is our new W. I would like to say this without using my voice or using the TTS. Then I input the W. Then in the same way, okay, this W is converted into linguistic features L. And this L, together with the trained models, can generate some new speech. Now, this is, the basic principles, right? So the whole idea is, in our basic understanding, we try to, we try to emulate the whole process of how we as humans produce meaningful speech. So we have a text in mind, okay, that we know the grammar of the language, so we know the linguistic features, all right? And then we have to know how to generate the sounds, all right? So this is what computer is doing, okay? But in the DNN approach, okay, you can see I put a big black box here. All right, so the input is just text, output is sound. And everything, in between, they are, just one integrated module. And then we call this an end-to-end approach. From this end directly to that end, I don't know what is happening in the middle, okay? So I make it black, and I just say that you don't know what is happening inside the box. It looks like that I don't like this approach. Okay, indeed, okay. I have been against this sort of approach for quite a number of years. Because I think, you give you a black box and tell me you can do this, you can do that. So then you don't tell me anything, right? So I'm not learning anything. So why bother? I'm, doing research or studying or teaching my students in university. I just say this is a black box, so I'm not going to teach you, okay? Because it's a black box. I don't know anything, so I don't teach you anything. So that doesn't make sense, okay? All right, but the black box power is huge. As you can tell, I think many of you, if not most of you, were kind of a little feel unexpected when you heard I say all those sounds were synthesized, right? So that was done by this black box approach, okay? So just like to hold the questions, okay? So university, we say, oh, we got to be open-minded. So let's, be open-minded just at least for this 1 hour, okay? Right, so the black box approach or deep learning approach is heart of today's artificial intelligence. and it's trying aim to build computational models to capture characteristics and also relation in the data. So we say data is king. And then if you can recall one of my slides, I say, okay, so the 25 hours of recording and 24 hours of recording to train, and you got that effect. So are you happy with that, right? But nowadays, it's so easy to accumulate 25 hours of speech. It's except that you have to keep talking, you know, but for a computer, it's so easy, right? And to learn the relation characteristics of data, okay, there are two very basic tasks. One is classification, the other is regressions. Of course, I'm not going to, you know, explain this in detail, but just from the word, classification is to decide whether this is a chair, whether this is a table, whether this is a light. Okay, so this is classification. For regression, you know, suppose you have to generate something continuous, right? Like, you know, if you in autonomous driving, okay, and the decision for steering is not that, okay, turn right, how many to the right? But that must be a continuum of numbers. So that's regression. Okay, we have to learn the regression, okay, from the data. And the so-called deep learning is that people believe, and it is also proved that having a deep structure of a computational model, we can model very complicated relation. That's the idea. All right, so in mathematics formulation, basically we have some input data, and then we have some output, say decision or continuum representation Y, and we have to, based on given X, we find Y. And then mathematical, this is a function. And then, so the machine learning is simply to obtain this function F of X. Okay, that's all the mathematics I will show to you. Okay. So what are the common sense or general approaches for us to obtain the F? You can guess, if you can, or search. If somebody gives you 100 candidates, say F can be this, can be that, you choose one of the best. That's possible. The other is by computation, you derive that, okay, in certain form. So that's what we do, in most of the time in machine learning, okay, area. We compute this or derive this X. And then this is done, okay, by the so-called deep neural network. So input is on X, and the out is on the left, and output Y is on the right. And then you see there are, several layers, several columns. They call layers. And then, so this is just for illustration. So 3 layers is not really deep. Okay, people are now talking about 6, 10 layers. And then the idea is that, if all these layers, they have nonlinear operation, it actually can compute very complex relation between X and Y. All right. Now, if we go back to speech generation, so what does it mean? Here we have input X and output Y. Now, for text-to-speech, the input, will be the text, right? And the output will be speech wave. Or more commonly, usually we don't directly generate speech waveform. We generate spectrographic spectrograms. So which is a time frequency representation of a speech signal. All right. So black box. I put some input text at the input of the neural network, and then at the output, I obtain spectrograms. If I have sufficient amount of recordings, I will have a lot of corresponding X and Y. I try to adjust some numbers in the network. I try to establish the relation, and then my job is done. Okay, so this is the general principles how people do DNN-based text-to-speech. All right, so all the linguistic features, they are learned from data. Prosody learned from data. If you build the models rightly, okay, even discourse level information, expression level information, style information, they can all be learned from data. One of the most commonly used text to deep neural network models for speech generation is called Encoder Decoder model. Basically, the encoder is to convert the input text into some kind of text representation. Now, the word embedding is very hot nowadays in the artificial intelligence. If you check out the website or literature, so embedding is everywhere. Okay, it's not a mysterious. So embedding is just, you can just take it as some numerical representation that you cannot understand being used to represent that something that you can understand. So you put in something that you can understand and become something you don't understand. But they are more powerful for certain tasks, okay? So that is embedding. Now, supposedly, if we train the model properly, the text embedding can capture not only, the alphabetical order, the word order or the phone, they can actually capture some context and long-term linguistic information, all right? But in a way that we don't understand, all right? And this text embedding will be put into another neural network model and converted into spectrogram. And then from spectrogram, we can generate a waveform. For those of you who are from engineering, you might ask, from spectrogram to waveform, you don't really need a neural network, right? It's just inverse Fourier transform. All right, but actually, for spectrogram, we only got the magnitude of the coefficients. Actually, it's not a complete information of the waveform, right? So people still use neural network to do the job, okay? Whether this is good or not, okay? A lot of signal processing people say, why do you have to do this? Because we know the mathematical relation between spectrogram and waveform, right? Why did you still use a black box to do that? Yes, but the results show that using such a black box with sufficient training data can do a much better job than you use your mathematical inversion. Because for the mathematical inversion, you are missing the phase information. And then the neural network can learn to compensate this phase information. Okay. And I mentioned a couple of times Testtron 2 model. Okay. You don't bother with all these modules in the beginning, in the middle. So the input you can see is a sequence of phones or sequence of graphemes. Okay. And the output will be a mouse spectrogram, and then further will be waveform samples. Okay. Right. So, but for such a basic models, if you train the models, then you use it to generate speech for any new input text. You cannot control that, right? Whenever you train the system, after you did complete the training, if I input the same text, like, I'm happy to see Professor Lee Ping. Here, if I put into text, there's no change of output. There will be the same speech being spoken for the same text. There's no way for you to control, the output speech. Say, if I would like to show, my, warm gratitude, to the host, so I might, speak in a different way. But the TTS cannot do that because there's no way for me to control. Okay, so what we are looking at in our recent research is on how to make it controllable. Okay. Now, the basic idea is we consider speech is the outcome or result of the combination or the contributions from a range of factors of variation. Now, speech has a lot of variation: acoustic, linguistic. In terms of acoustic, we have environmental, noise, right? Prosody, expression, all these sort of variations, speaker, right? And you can list thousands of these factors, okay? But we don't, they're all sort of playing their roles all together and finally give you a single speech signal, right? So how can we separate these factors? That is what we mean by disentanglement or factorizations. Now, with the properly designed neural network models, that here we are, moving away from the approach of black box. All right, we try to, by applying proper training procedure and proper data arrangement, we try to separate these factors. All right. In terms of style control, we like to have some kind of factors that are related to style. But if you check, so I checked the dictionary, I Googled the dictionary on style. Okay, what does it mean by style? There's no precise definition, right? So here is our, very simple, and so don't take it as any formal definition. So this is my suggestion. Okay, so we consider there are three basic factors of variation in a simple speech produced by human. The three factors are content, okay, the linguistic content. Second, speaker characteristics, the voice, mainly the timbre characteristics, okay, whether it's male or female or sort of, how do you say, hoarse voice, it's a different kind of voices, speaker. The other one, all the remaining variation, we all attribute to style, okay? So in other words, dialects, we just say a style, okay? Or, so, please do not criticize me at this point. So I say, this is just, for engineers, we have to define the problems, okay? I would say the style is something, okay, that are not contributing, okay, to the basic, linguistic understanding, and then to the recognition of the speaker. So all the others are style, okay? All right. So by style control, so we hope that we can disentangle the style factor from all the other factors. So we get something, and this is style, and this is embedding, and this is a bunch of numbers. By changing these numbers, I change the style. Does it make sense? Okay. If these factors are effectively extracted to represent the style, so-called style. Okay. Now there are a lot of works that need to be done. This is not a solution. This is just a proposal. Okay. So content, speaker, and style. And then at the red dash line, okay. Now if we don't change anything, suppose we have input speech, we obtain the content factor, speaker factor, style factor separately. And then if we recombine these factors intact, I mean, without any change, we should obtain the very original input speech because we don't change anything, right? Okay. But if we change the style embedding, suppose we can change the style of the output speech. If we change the speaker embedding, presumably I can switch to another person's voice. Now, usually we don't want to change the content, right? The content is just the basic function of synthesis, right? It's always changing, okay? So I'll give some examples, you will have a better idea, okay? All right, so here in this case, I show you, say in the green and then the yellow box, you know, if we look at the middle one, if I take a reference speech, for example, now if there's a TTS system, okay, that is trained on my voice, okay, then I take another speech utterance from Professor Peng Gang, say for example, and then from Professor Peng Gang's speech recording, I extract the style embedding and put this Peng Gang style embedding to substitute my style embedding. Then I suppose the output speech will carry Peng Gang's style with the content of the sentence remaining the same. Does it make sense? Okay. So all this can be done with some kind of smart ideas of training our neural models. Now here there are a lot of details of algorithms, but they are one of the ideas I think should not be difficult to understand. Now here you can see that I have, in this model, I have a content encoder and style encoder, which produce a content embedding and a style embedding, right? Now suppose content embedding should contain only the content related information. That is the phonemes, the order of phonemes, things like that. And then supposedly, okay, the style embedding should contain only the style related information and should be independent of the content. Okay? So how we can guarantee, how we can ensure that the style embedding contains only style information and the content only for content. So we use a phone classifier and what we call an anti-phone classifier. Now the idea is if the content embedding should be very good at representing phone information, linguistic information, then if we use this content embedding for phonetic classification, it should be very good, right? It should be able to tell the difference between R and E and right? Makes sense, right? So I try to optimize and push up the performance of this phone classifier to 100% accurate. Then I can guarantee the content embedding contain mostly, phone related information. Similarly, for style, supposedly it should mess up all the phone, right? I give you a content, a style embedding. I say, this one is different from that one. Okay. Now you should not find any information related to the phone. If you use this content style embedding for phone classification, it should give you a random guess result. Okay, now that's the basic idea. Okay. So we call this collaborative learning, adversarial learning. Now all these fancy names you can check out on the literature of machine learning. Okay, let me show you a few demos. Now here on the top there are two ground truth audio, original speech. I play these two first.
Those who were the oldest offenders sentenced to transportation and who had narrowly escaped the penalty of death.
All right, you just got a sense of how this lady read. And the next one.
The court was, however, prepared to consider Lord John Russell's proposal with regard to the cost of rebuilding.
You get a idea how they might be different in speaking style. Okay, now this one is I keep the same content of the first one, and I try to put up the style of the second one. So let's listen to the second one again.
The court was, however, prepared to consider Lord John Russell's proposal with regard to the cost of rebuilding.
Now we put this style on the first utterance content.
Those who were the oldest offenders sentenced to transportation and who had narrowly escaped the penalty of death.
The pitch actually is, lifted. Okay. You may say that there's some change, but whether this is exactly the style of the second one is hard to say. Okay. This is one of the work of my students. Now, the other issue is that I say content embedding is just a bunch of numbers. Style embedding again is a bunch of numbers. You don't know what it means. So if this is the case, how do we do the control? Right? So there's number in the embedding, which is 100, and make it 90, and then make it 10. What does it mean? We don't know, right? So we cannot interpret this sort of representation, which are not so useful then. Okay. So for this continuous value vectors, one way to make it more interpretable is to quantize it to a finite number of choices that we can check out, how, so whether any of this context representation really mean anything, okay? So this is how we do that is, if for those who have knowledge about machine learning, we kind of vector quantization by using neural network, okay? So the continuous one representation, continuous value one will be matched with a dictionary, okay? And then we got some discrete representation, okay? And then for style control speech generation, so we will sort of adjust, okay, some of this representation, okay, and we substitute some of the solution, we alter some of the representation that hopefully we can make some meaningful change. Again, audio. Now, the first one, example, okay, this is the text content, and this is the original speech without any change.
The fatigue would be too much for your end.
It's too loud. Let us listen to that again.
The fatigue would be too much for your end.
And then the second one is that we pick one of the context representation. We think this is representing a particular type of change.
The fatigue would be too much for your end. The fatigue would be too much for your end.
So if I change the style, it's just like a token, okay? I take the original token and put another token and make this word longer and emphasized, Same for the second one.
I do not know what it is all about.
And the original one will be,
I do not know what it is all about.
all right? So this is what I mean by interpretable. So if I really want to emphasize this by lengthening that, I can do just, change the token, okay? And this is doable. All right, so I think we are running short, 5 minutes. Okay, they're all the same type of, research. Okay, perhaps I can, this is one that we do recently. It's called seamless editing of speech audio. Now imagine a scenario, somebody give you a long recording, or you made a long recording, but after, at a very late stage, when you like to use this recording, you find that some part is actually not correct. You want to change it, but it is not possible for you to redo the recording. Okay, what do? If a Microsoft Word, you just open a document, change the word, save. That's it, right? For speech audio, right? Okay, so you don't have the recording machine, right? So how are you going to do that? You can use speech synthesis. All right. So again, some neural network models, fairly complicated one. The key idea is we like to, use the context both before the changed region or after the changed region, the edited region. Okay, so let me show you some example. 普通话 probably. Okay, this was the original one.
这些差异和不同，实际上就是横亘在穷人和富人之间的一道分界线。
This is the original one. And then this one is insertion. I insert 社会的 okay.
这些差异和不同，实际上就是横亘在社会的穷人和富人之间的一道分界线。
Would it be very natural? Is it? If I don't tell you, you might not tell the difference. Whether I can, now of course this might cause some, concern of integrity or fake. So we don't consider this problem. Okay, let me quickly go to the final part, which I think is very interesting. So using actually these two applications, they are all basic TTS for a particular person. We haven't applied all of our style control algorithms to that. Okay. So the first one is a child storytelling. So what we did, we collect recordings from a professional trained storytellers, and we caught about 6 or 7 hours of speech. And then we use a modified Testtron 2 model. We develop a storytelling TTS. And then we can input other storytelling text. These are in Cantonese, and you can, check some audio samples.
故事嘅主角咧係一對小朋友，家姐個名叫做慧賢，細佬個名咧叫做文軒。有一日，慧賢嘅爸爸媽媽一齊返到屋企，媽媽偷偷地咁樣拎住一個好似屋仔咁樣嘅袋，入到門口之後咧就匿喺爸爸身後啊。
So this is synthesized, all right? Actually, this is a new story, all right, of the same speaker. And then we got a demo of the app, actually on the app. So now Matthew is laughing. Matthew did that, okay. And then, so actually the user can change the content of the story. Say, Manhin, you can change to Pangong, okay. Then, you can, change. So the child become the 主角, okay, of the story, okay. So that will be engaging better the user, okay. The last one, Matthew know that I'm going to share this. Okay, this is a recent story. Okay. Now, I'm not quite sure whether you can read this 廣東話嘅 text post. Basically, it's a post in late June of this year on 連登, okay, 連登 forum, okay? And then somebody says that there is an adult who is going to receive a major surgery and then have the whole voice box removed. After that, the patient will not be able to speak at all. Okay? And then they say, is there anything that people can help? Of course, we don't know this person. Okay. And then one of my students, who is Matthew, saw this post. So you know that Matthew is a 連登 user. Okay. And then call me and say that, Professor Lee, shall we help? Okay. Then I say yes. And then in 2 hours, we got in touch with this patient. And then in the second day, so this is the time frame. Day 0, we know this, we got in touch with them. And then the day 1, we started recording. And then in other following days, okay, we got more recordings from the patient. And then slightly more than a week, the patient cannot speak anymore because the operation is done in day 10. Okay. And then after 2 months, the end of August, we made a TTS system. And then 1 month more, we make a tailor-made app. And then I'm very happy to show you. Okay. So this one is the original recording. And then just give you a background, the patient actually, the cancer was recurrent because actually the patient had surgery some time ago. So part of this tongue already, small part of it already removed. So she could not articulate perfectly. Okay, you can tell from this original recording.
其實佢已經俾嘉莉發現咗啦。嘉莉雖然冇辦法同阿莉講嘢，但係佢已經興奮到不得了啦。畢竟佢發現咗呢一條難得一見嘅美人魚啊！佢拎完張相，周圍同人炫耀。佢話啦：我真係見到美人魚啊！睇下，我仲偷偷地同佢自拍添。
Now we got 5 hours of such recording, storytelling, colloquial, and then, at 2 months later, we got this system, and this is the outcome.
你要專心仰賴耶和華，不可以靠自己的聰明，在你一切所行的事上都要認定他，他必指引你的路。
This is a Bible sentence, and the other one.
佢先將黃色星星還翻俾欣欣，同埋同佢講對唔住。
Okay, and then we developed an app like this in October, and then we sent this to the patient to use, and then a few days later, I got this WhatsApp message, voice message from the patient.
李教授和各位同學，大家好，非常感謝大家為我製作呢個程式。我知道大家都好努力咁改良更新，喺醫院聽到醫生話會推介俾其他病友。假如有用到我嘅地方，我隨時都可以幫手。好似教授講嘅，呢個係一個緣分。
Okay, so this is what we can do, up to the end of last month. We can do better, okay? So, and I'm sorry that I take too much of your time. And then, so I was, this actually not so important. So thank you very much for your attention.
Thank you very much, Professor Lee. In the interest of time, we will now move on to the second lecture by Professor Lee.
Hello, hello. Okay, so good afternoon, and thank Prof Wang very much for his kind introduction. And in order to catch up our schedule, I will cut my story in short. So my title is Tone Recognition by Electronic Brains, that's computer, and perception by human brains. What's the difference? And what's the similarities between them? So first, I will introduce a little bit about what are the Electrons. And these figures was made by Prof Wang, and you will see many years back, right? So for tone language, when we change the pitch patterns, we change the meaning. The same as we change the vowel, the constant. And we all know that the pitch pattern is the main feature of the Electrons, but other acoustic features, for instance, the duration, and in particular the intensity profile, are also correlated with Electrons. The most striking sample is the Mandarin tone 3 in citation form. For instance, ma, we see the pitch pattern first go down, then go up, right? Actually, the intensity profile also follows this pattern. It's highly correlated. And here, two figures show, right, the pitch trajectory of 6 Cantonese tones, the 6 long ones, and the 3 short ones on check syllables. Right? This is for Mandarin 4 lexical tones. Then how to identify them? So here we have 2 objects, right? So we can see they have different shape, different color, also they have different tastes, right? We can use these features to distinguish them, right? Then we can judge, okay, which is banana, which is apple. So the above thing is the features, and the bottom one is the classifier. Then how computer recognize tones? We follow the same rule. We have first we have to select a set of tone-related features, as I have just introduced, right? The pitch patterns are the primary feature. So we will use their values, as well as the duration of the syllable, and the intensity profile of the syllable, and so on. Then we need to choose a classifier. There are many choices, of course, right? Deep neural network, Prof LEE Tan has introduced just now. Support vector machines, I have used many years back. And after that, we have to figure out the parameters of the classifier. That is training, right? Finally, we can use the trained classifier to recognize tones. So features of an unknown tone token as the input, and then go through the trained classifier. Then the output is the tone identity. This is the basic ideas of tone recognition. And we have used, right, the tone-related features like this, right? Here we show the target syllable with its preceding context and the following context, because we know co-articulation, right? So we choose F0 values as well as the intensity profile and the duration. We use these features as tone-related features in our system, and then I will show you the computer matrix of our computer tone recognition system. Here we just show you the result of Cantonese 6 long tones, right? So we can see the accuracy varies a lot according to different lexical tones, right? The tone 1, the high level tone, right? We have got the highest accuracy, about 90%. And for some tones, we can see this one, right? Tone 5, the accuracy is very, very low, only 34%. And the overall accuracy is 71. Okay. And when we check the computer matrix, we can see for some tones here, for example, tone 2, the high rising tone, right, was misrecognized as tone, tone 3, the middle level tone was misrecognized as tone 6 with a very high percentage, about 20%, right? And for tone 5, the low rising tone, right? It was misrecognized as tone 2, the high rising tone with high percentage, 24%, right? And the low level tone, tone 6, was misrecognized as tone 3, the middle level tone, with also with a high percentage, right? So we can see these are the error patterns of a computer tone recognition system. And then we look at whether human brains can do a better job. So we extracted these tone tokens from the computer speech and have done a perception test. First, we cut the target syllable out without preceding and following context to see how human brain could achieve. We can see its accuracy actually is very, very low, right? Only 41%, and about 35%, right, were incorrect. And with a large percentage of samples the subject cannot decide actually. Then we added the preceding and the following top context. And now we see the accuracy has been much improved, right? From 41% to 68%. And the uncertainty has been largely reduced from 24% to 5.8%, right? So for human tone perception, the context is very, very important, right? And then we move to another study, Cantonese tone perception with and without context, right? By Shaojing and Professor Zhang Sanzai in our department. And in their study, they recorded 60 monosyllabic words contrasting 6 Cantonese long tones without the 3 short tones. And in that recording, they embedded the target syllables with the carry phrase. And they have two experimental conditions. Right? In one condition, the 6 target words were presented in isolation to the subjects. And the other one, right, the same set of 60 target words was presented with corresponding carry sentence, a legal jihad. And in this study, they include 2 groups of subjects, 23 amnesias, those who have speech deficit, in particular in music domain, and 23 age matched. Of course, the other matched factors, so-called control subjects. And then now we see the results, right? In isolated condition, the accuracy is lower than the accuracy with context, in particular for the controls, right? For the amnesia subjects, there are no big difference. Okay, now we get 2 points. The first one, can we use tone recognition by computers? Or can the tone perception by human brains are really difficult, right? You see, with context, without context, even for the controls, the average accuracy may be around 70%. It's quite close to the numbers we have got for computers, right? Even with context, the accuracy may be around 80, not very high. So can this tone recognition or perception is challenging? The second point is the context is crucial for both Cantonese tone recognition by computers as well as by human brains, right? So this is the point I have just made, right? And we know that some tone pairs which are confused the most, right? The 2 level tones, middle level, and the low level, and the 2 rising tones, right? The high rising tone and the low rising tone. And then we moved to another topic, the context effect of Cantonese level tones, right? We know the level tones are confused severely. So we made, in addition to speech context, we have made non-speech context, but they share the same F0 information to see whether the non-speech context with the same F0 information as the speech counterpart have the same effect. And also, we manipulate the F0 by this way. One, we keep the original F0 contours. Another, we flattered the F0 contours. So I have samples below. And in order to better reflect tone variation across speaker, right? We have adopted recordings from 4 talkers, 2 female voice with different F0 range, and 2 male voice also with different F0 range, right? And we embedded our target syllable in the middle of a carry sentence. Right? Here are some our manipulations. And here is a sample of our speech condition. which means the target syllable is embedded in a speech context. Let me try.
請你讀意嚟聽下。
It's a clear speech sample. And here is the sample of the speech target with non-speech context. Right. The target is the same. And here, now in this sample, we flattened the F0 contours of the context part.
請你讀意嚟聽下。
These are the samples. And we know for a given level tone, without context, it's really very difficult for us to determine whether it's a high level tone, middle level tone, or low level tone, right? Here, the same pitch pattern. If the F0 range is like this, then clearly this pattern is associated with the high level tone, right? And in this case, then this pitch pattern is of course associated with the middle level tone. And this one is clearly associated with a low level tone, right? So with the help of context, we can differentiate them, or else low A. So in our experiment design, actually, we keep the target, the pitch pattern of the target syllable unchanged and manipulate the F0 level of the context, right? By lowering the context, then we expect to see that the perception of the target syllable will be the high level tone, right? When we raised the F0 level of the context in like this way, then we expect to see that the perception of the target tone should be the low level tone, right? And then we, right, for analysis, we code the subject response as this. If the subject perceived a tone token as a tone 1, we code it as 6, right? Tone 3 as 3 and tone 6 as 1. Okay, so with a lowered F0 context, if a subject correctly respond as we have expected, the most of his or her responses should be tone 1, right? And then the final score should be close to 6. On the other side, right? If the F0 of the context is raised, then expected response should be tone 6. And averagely, the perceptual result should be closer to 1, right? But this is the real case. We come to our result. So we have 5 different types of contexts. Isolated one, without context, that means, right? Non-speech context with a flattened pitch contour for the context, right? Non-speech context with the F0 contours unchanged, right? And we have 2 speech context conditions. And we can see only for the speech context conditions, right? When the F0 values of the context is lowered, right? The perceptual result is close to 6. Right? This is what we have expected, right? When the for the raised context condition, right? the perception result is close to the other side, 1. Right. So this figure shows clear context effect for Cantonese tone perception. And also, we show the result of identification rate, because we know when the context, when the F0 context is raised, right, then the expected response will be the low tone. If a subject responds like this, then we say it's correct. And we see with the long speech context, either with a flattened F0 contour for the context or the original F0 contour of the context, right? More or less guessing, right? This dashed line, right, is at 33%. The guessing, the trace level, right? Only with the speech context, right? The accuracy is higher. And we can see with the original contour kept, right? The accuracy is higher than the flattened condition. And then we move to another question, right? Because previously by behavioral experiment, we know, okay, the context does influence the level tone perception. And when it occurs, right? By using behavioral experiments, we can only see the final output, right? By looking at the response patterns. And from the onset of stimuli toward the subject's output, there is a long duration. Right? Then what happens in the brain during this period of time? We use EEG to look at this issue. And the manipulation is highly similar to what we have done behaviorally, right? We have, in this way, we have 2 speech conditions, speech, long-sense speech, and speech meaningful. Here, speech meaningful, legal zihai, right? You say meaningful sentence. Here you will see just several syllables combined together. And in order to facilitate the ERP calculation, we insert a sentence in between the context and the target. And we also analyzed the behavioral patterns of this ERP study, and we replicate the behavioral patterns for long speech context. You will see, right? The identification rate is almost at the trace level. Only with the speech context, right? The identification rate is about 80% in this study. And we found for the ERP patterns, right? We identified 3 ERP components in this study, N1, N400, and LPC. LPC means late positive component. And for this time windows, we found a significant context effect in P300 as well as LPC, right? Because behaviorally, we know the speech context showed a significant context effect, but a non-speech context did not show any context effect, right? So for these 2 ERP components, we find, okay, this is imputed from the non-speech condition, right? It has a significant difference between this non-speech condition with the nonsense speech condition, as well as the significant difference between this long speech condition with the speech minimum condition, right? So at least we can say that some normalization process has happened during this time window. And for the N1, the earliest ERP component we have found, we did not find a consistent difference, right? Although by eyeballing, it seems, right, there are some difference. But statistically, this difference was not significant. And then we have adopted another paradigm to look at this issue again. So in this study, just published this year, we first pick up the three most ambiguous stimuli from the tone continuum. Because previously, right, the target tone is always at the middle level tone. It's a typical one. And this study, right, we have made a tone continuum from the high level one to the middle level one. Because we believe for the most ambiguous tone stimuli, they will be more sensitive to the context, right? Therefore, we first, right, determine the boundary of this tone continuum by tone identification test. That is a part of a categorical perception test. And then we chose the three most ambiguous stimuli from this continuum for the EEG experiment. And in the EEG experiment, the subjects are instructed to click the mouse only when they thought that the target was O, right, with the high level tone, which made the word identification task resemble the go-no-go paradigm. Previously, we use a simple or straightforward tone identification paradigm. Now, it's a go-no-go paradigm actually. And in this paradigm, we find another ERP component. First of all, behaviorally, right, we confirmed there is a context effect because in this study, with the F0 manipulation, just with either the high F0 context or low F0 context, right? And behaviorally, we found the contrastive context effect replicated the previous patterns, right, in general. And in this study, we also used a new ERP analysis called RITE, residue iteration decomposition, divided by a group of Hong Kong U. And this axiom can decompose the ERP signals into three component clusters, so-called stimulus-locked cluster. That is S cluster, usually occurred earlier, for instance, M1 component. And the middle one is a central cluster, C cluster, referring to the intermediate processes between S and R. R is the R cluster. That is the response-locked cluster. And in this study, we found an ERP component in the C cluster. That is the P3 component. And we found a significant ERP difference in P3 component here. So in combining these two ERP studies, right, N400 has been hypothesized to reflect violation of semantic expectancy in general, right? And in our study, any word can appear after context because our context is semantically neutral, right? Therefore, it's unlikely that N400 elicited in our study may reflect semantic expectancy violation. Then we think that the N400 in our study, that is in a time window of 250 and 500 milliseconds, involves programmation and lexical retrieval, right? Which overlap in spoken word education. This is our explanation of the N400 component. And in our recent study, the P3, sometimes called P300, usually mean the same thing, observed in a very similar time window, 220 and 500 milliseconds, right? And this component could be the combination of the inhibition to the response to the level tone, and the detection of the comparably rare word trails, right? Because the subjects were instructed only to response to word, right? And when the context with high F0 value, then the perception, the expected perception would be word, right? And the subject has to hold on the response. So it's kind of inhibition, right? So these are two explanations. And right, we have not found significant difference among the edit time windows. But anyway, we should be cautious, right? Absence of evidence is not evidence of absence. Probably when we adapt other paradigms, we can find context effect in edit time window, for instance, P2 window, or even N100 window. So we'll look at these new things in our later studies. And the open issues here. So linguistically, pitch height and slope can be used to represent lexical tones, right? So we have drawn tone charts many years back. The left one is the tone chart for Mandarin, and the right one is for Cantonese, right? In this study, we use two parameters, the pitch height and the pitch slope, to represent each tone token, right? And we found, okay, the Mandarin for these tones separate very well. However, for the Cantonese tones, right, there are lots of overlaps. In particular, for the two level tones, middle level tone and the low level tone, and the two rising tone, the high rising tone and the low rising tone, right? And then one asks, how lexical tones are represented in our brain, right? There are several theories, of course. For instance, the abstract one, right? And the example-based one, right? For the abstract model, each category is represented by a single abstract representation, right? The average pitch height as well as slope. For the example-based model, each category is represented by a set of multiple examples, or simply memory traces of each input. Right? This actually lots of debates, and probably is a mix of them, right? And which model takes the major role depends on the situation. Now, how you are familiar with the talker, or the typicality of the talker, and so on. So due to time limit, right, I will stop here. So thank you very much for your coming.
Well, let's still take a few minutes for comments on either paper that we've heard this afternoon. Did you have a comment? Okay. Anyone? Toby, anybody from the chat room? Okay. We have over 100 participants on the chat room as well. Professor Lee Ping there.
Hello. This is a question for Professor Tan Lee. You mentioned about the deep neural nets performing all these wonderful tasks, transpositions and transfer of prosody onto contents, which is great advance and has a lot of practical engineering applications. And at some point in your talk, you mentioned that the neural nets with nonlinear functions and multiple layers basically is a black box. And somehow the introduction of encoder and the decoder could help us to at least illuminate the black box a little bit. I got a little bit lost in there, so I'm wondering how the encoder and decoders actually help us to understand more deeply and theoretically about the features of language. So it's a big question. I hope you can give us some insights. Thanks. Thank you, Professor Lee. I know that I didn't do a good job at that part. Basically, the idea of encoder and decoder is like a self-generation process. Say, if we have some kind of pattern, input pattern A coming in, and then through a complex network, it will generate back the same pattern A. Now, it looks like it doesn't really do anything in the middle, okay? However, the encoder and decoder, they are specially designed such that they would generate, so the encoder part, they would generate several different components. Of course, how to train the network to extract these components or make these components meaningful is a big topic, but the general idea is like this, right? So if these intermediate representation components, if they all go to the decoder intact, so without any change, so suppose nothing happened. But these intermediate components, you can see somebody will use the concept of bottleneck, like, so you kind of make a bottleneck in the process so that all the irrelevant information are removed. So you can see these are several bottlenecks. So all the unwanted information are removed from each of these representation. But they all combine, they will get in the original output. So that's the rough idea. But for the training, there are many different approaches, right? So.
Yes, back there.
This is a question for Professor Lee. So I read in the literature that the current development in the brain-computer interaction, that we can somehow to determine the things a person wants to say through, for example, eye tracking technique by seeing the tokens on the screen, or by classifying their brain activity, for example, the EEG, so that we can somehow know what they want to say. It seems a kind of very good research direction if we can combine this kind of brain-computer interaction with the technique you described, so that we can directly let the patients who cannot speak to speak naturally without even inputting their content of thought into an app you developed. So actually, this is not a question, but I want to hear your comments about this direction of development.
You are absolutely correct. And then, brain-computer interface has been advanced quickly. And then I guess Professor Peng did a wonderful job in that area when he was at CU, I guess. And also the TTS technology is also, making advancement quickly. So I'm really happy to see all these, things coming together to really, help people. You are perfectly correct. We were excited that, we can reproduce the patient's voice. And then when we listened to the first sentence that we synthesized, we were so exciting. And I think the same for the patient. But when we, try to use this in daily life, as I just talked to Professor Wang, the patients still have to type text, right? Or write on the writing pad. So that's, well, it's not for instantaneous sort of speaking use. A lot of things that can be done, follow up, like somebody will do SEMG, right? Surface, the muscle signal for articulation. And then brain computing control, of course, is wonderful. Yeah, but I really don't know much about this area. Yeah, thank you.
I also have a question for Professor Lee. As you have mentioned, that the number of layers of a deep neural network can be from 3 to 6 or even more. Then, are there any general rules of determining the number of layers as well as the number of nodes at each layer? Right?
Yeah, I would try to say that I'm not a researcher in deep learning. I'm just a user of deep learning. So I really dare not answer this question. Well, I think there's some theoretical work being done. But nowadays, for those people who are just like me that we probably just, naively say that we try, right? So, and then, but that's definitely not a good idea. Not really, for recommendation, right? And also, I would like to add a final word that training all these neural things take a lot of computation power. That means taking a lot of electrical power. That is causing a lot of environmental problems. Okay, so this is something that I keep sort of cautioning my students. So when you publish a paper, how many hours of GPU computation have been running, right? It's not a matter of money, all right? So whether this is really needed, okay, that's a big question.
I have a question for Professor Lee. And based on your research, you show that your model tries to separate the features of content, speaker, and style, and your model does it very well. And based on my understanding of speech perception of human, and once speech cues like pitch, it is important for the perception of all of these 3 dimensions. So I want to know how your model can do this to like separate it so well. And another question is, will your work inform us about how like which acoustic cue is more important for our humans' perception of speaker, and which cue is more important for the style or content?
I think the quick answer to the first question is that the model actually does not do the job very well. Okay, so for control purpose, so what we can do is that we got something that we claim to be related to style, and then we change that. We can change somehow the style a little bit, but I think conceptually we cannot separate style and speaker, right? So that's for sure. But we have to make this, an engineer, we have to make the problem simple and well-defined, then we can do the work. Sorry, I didn't get your second question. Probably we can talk a bit more offline. Would that be all right?
Okay.
Yeah.
Hi, Professor Lee. My question may not about the speech. My question is that, is there anybody or researchers doing researches about solving the problems about pragmatics area or to make the computer much smarter of handling people's sentence in about the culture meaning or some pragmatic way? Cultural meaning, for example, cultural meaning to make the computer smarter in that area.
I'm sure, I'm not very familiar with this area, but the research on natural language processing is, it's very hot, okay, with the deep learning or artificial intelligence technology. So I'm sure there are people working on that, but honestly, I don't know. Yeah, thank you.
Thank you.
Any more comments? If not, let's thank our 2 speakers one last time.
Thank you.
One more moment. It is a custom of the lecture series that the speakers be rewarded.
Thank you.
One more. That's